Afternoon again. So my name is Gustavo Neumann. I have been working in Braskem in the last 20 years, as I said. And during 11 years, I have worked as modeling and process control engineer. After this, during 7 years, I was automation coordinator. And the last 2 years, I'm playing with data and loving doing some comments as subject matter expert for automation group. And Braskem is the largest producer of thermoplastic resins in the Americas, and the largest one producers of polypropylene in the United States. Braskem has 41 industrial units, the most part in Brazil, and 10 units in North America, 4 in Mexico, and 6 in the United States, and 2 plants in Germany. We have offices and clients in 100 countries. You have more than 7.5 employees, team members around the world. Some numbers of financial issues, and our partner in this project is Radix, and José Guilherme will present.
We'll just talk quickly a little bit about Radix. We are now a 700 employees, a Brazilian company. We have 5 offices, 3 in Brazil. The most part of our employees are in Brazil. We have 2 offices here in United States too. And our main business is engineering software and doing projects where these both subjects come together to solve our customers' problems. So this will be the case that we will show today, this predictive maintenance. Gustavo will introduce a little bit about the project, and then I'll talk a little bit of the technical details.
In the 2017, Braskem CEO encouraged people to start developments of initiatives related to digital transformation. A lot of initiatives started in this time, but without a centralized coordination. In May of 2018, Braskem created a digital center to conduce portfolio, train people, manage changes, define good practice related to digital transformation, share lessons learned, and centralize data science issues. During this digital transformation strategy, in November of 2017, we mapped an opportunity related to predictive maintenance and start a journey developing some machine learning models to equipments. And the objective was identify failure modes, deviations, and correlation between their variables, their measurements. And the first step was understand the bad actors and the equipments with enough instrumentation to get the data and start the development of the models. We define a MVP in this time, selection of 6 families of equipments, and start this development. The first step was the vendor selections. 8 companies participate of the evaluation. We selected 2 partners as part of these developments, according of some requirements. For example, an open platform, an open code, because we understand that we have flexibility to do more things with these developments. In this MVP, we selected 2 of these companies and the 2 developments in parallel. 3 equipments for each one. During 6 months, we developed these MVPs in 5 different states, different sites in Brazil. And was a challenge because we have a set of meetings a set of deliverables to manage in parallel. And after these 6 months, we had 6 dashboards to see a new view of the expectation of results and a lot of lessons learned. And after this, we define a new strategy and select the Redix as our partner. And this start the expansion of these developments. With sorry, again. After the scope review and the start of the expansion phase, we reselect the equipments and define a new scope. We have some challenges in this project, in this first part of the project. The predictive models is not so difficult because we know the strategy. If you have data, you know how to train the models. But we have some challenges related to the culture, to the people, because everything is new, a new way to work. We need to redefine the integration between the new workflows and the traditional vision of this way to work. We need to redefine our structure, IT, OT structure, infrastructure, to have these dashboards available. And in development, we have 2 other things. Is a centralized PIMS, Process Information Management System, and a new Center of Excellence developed in construction to sustain and maintain these new models, these new machine learning, and new dashboards. Our scope is a cloud data, cloud platform to run these predictive models in order to monitor 54 assets distributed in these 6 different families of equipments. The investment is around $1.2 million, and the return as saving is almost $5 million per year. So José Guilherme will present details about this development.
So as Gustavo was saying, we participated in the construction of the 3 equipment families MVPs. And for this expansion phase, we have 54 selected assets distributed in 6 different plants. So the size of the challenge was completely different from what we did before in this MVP. So how to address this size of this challenge and how to solve and to bring more value to Braskem regarding the asset life cycle, the assets maintenance, and the production efficiency. So what we learned from the MVPs is that the Braskem has the domain specialists in-house. So we talked with some personnel with 20, like Gustavo, 30 years of Braskem running the same plant. So they have a lot of domain knowledge. And also a key factor of the success of the project in the first phase was the engagement of these plant personnel in the development of the solution. So if you have the guy that at the end of the day will look at the alarm and have a decision, and this guy is involved since the beginning of the process, choosing that equipment and looking to the data, helping the data science in the models, and choosing what will be shown in the dashboards, this guy will treat this solution as if it is its own. So the first lesson that we learned and we applied on this phase was to bring plant engineers and operators to the table to talk and to have a high participation on this project. The second one is with 54 equipments and in 6 different plants. All of them had different failure modes, different opportunities we can apply these technologies but we had to prioritize and choose what would bring more value to the company, and choose the items, the failure modes, and what would really impact the company results. So then we choose to organize the team in 3 different parts. So the first one, we built an engineering team with large domain knowledge from Braskem and from Radix side. And these previous experience in different industrial projects, and with consultants with large knowledge in specific kinds of equipment. So this was the first pillar of the team that was executing the project. The second part was data science. So one thing that we did to reduce the gap between the engineering plant guys, our engineering guys, and the data science was to use the data science with engineering background. So we had some data science with chemical engineer, mechanical engineer, control automation engineering background that became data science. So this was one of the key differences and levels of the project, and they could talk together with the engineer and to the Braskem plant personnel better. And also the third pillar of the project was the software development team that was responsible to build this platform that was built to run these models in the cloud in real time with data being fed from the plant. So we also choose to use software development team with industrial and engineering background. And we divided the problem from the data science perspective in phases, in steps. So in some cases, we had 8 equipments for a similar equipment family. So we choose one equipment and start the modeling and do the analysis, and then replicate the solution. What's similar, we can replicate. What's different, what we can take and learn about what we did in the previous equipment. And doing these in steps gives the opportunity to improve inside the project. And also in the software development, we did in an agile way, talking to the end user and giving them the perspective and giving them the opportunity to choose what they want to see in the screens, what's most important for them. So it was a big differential too for the project. So talking a little bit about the solution pipeline, as I said before, the engineers and the domain experts, they played a really important part in the process. So all started with engineering assessment of the equipment. So in this first phase, the Radix engineers and Braskem engineers sat together to look at the equipment, look at their documentation and the data available, to see if the equipment have enough instrumentation to do a failure mode effect analysis on how the critical failure modes develop in the plant, what are the impacts on the process. And this is the first step, this engineering assessment, and to look with detail to the equipment. And in some equipment, in this phase, we realized that some equipment didn't have enough instrumentation. So what we did was to emit recommendation so that Braskem can buy the sensors, can buy and install the instrumentation, so that these equipments will be monitored in the future. So after this first assessment comes the look at the data, and also, as Tom was saying, the domain and the subject matter specialists, they have to play a really important role on this phase. They know the data, they know their equipment. And so one thing that we did was to look into the data, to the available data, but also to look at first principle equations, engineering equations, and phenomenological and the dynamics of the equipment, and bring all these together with process data, the failure records, the maintenance plan. So all of these data was used to select the critical indicators for the failure detection. So in this failure detection selection of the critical indicators, the domain experts and the data science together decide what strategy they will be pursuing. So in some cases, I think we saw this in different presentations on this conference so far, that machine learning and artificial intelligence is not magic. Some people think that it's magic, that we'll have the data, put it in the box, shake the box, and the solution will come right away. Sometimes if you have big data and tons of terabytes of data, maybe it's the case. But for industrial solutions and industrial plants, that's not the case. We have old equipment with lack of instrumentation. We have problem on the data. So in some cases, we looking at the data and using first principle equations, we saw that the data guidance and the data-driven uses of these indicators was already enough to detect some failures and was already enough to give some important alerts and some important information to the operators to take a better decision. So what we're trying to do is not use machine learning for everything. In some cases, the engineering and the data-driven use of engineering knowledge was able to solve the problem. And I'll show at the end one small example of this. And in machine learning, we had different techniques and different ways to choose. And in this part of the project, the engineers and the data science together, they decide what they will be trying to do. In some cases, we have a large data sets and a large number of failures events. So we can try to use a similarity detection kind of models, that you have a model that will learn what is the pre-failure condition, how it looks like, and compare with online data and see if it's most probably to be a normal condition or a pre-failure condition. But sometimes we don't have this amount of data to do this kind of modeling. Some critical equipments that was selected to the project, we found sometimes that they have 2-3 different events of failure. So how you build a reliable data science model with this extremely unbalanced data set? So in some cases, we went to a method to create a model that learns the normal condition and learns what the equipment operators in when it's not in the pre-failure condition and which is operating in the normal range. So we call it's something like a digital statistical twin. And with this, we can create a model that is predicting one key variable of the process, and we are comparing these real time with the process variable that are coming from the data historian, and we can look at the difference between them, and with this difference, we saw that we were able to detect the condition and the degradation of the equipment. So this will be one of the examples I'll be showing to you at the end of the presentation, that we saw that even with the low number of events failures, we saw that 20, 30 days before the failure, this discrepancy between what the statistical twin was saying and what the process variable from real time was saying was increasing, and we were able to use a linear and throw an alarm to the operator that the equipment was in a pre-failure condition. The last one is create a model to estimate the remaining useful life. So we create a model that calculates how much time before the failure it is each data point, and then looking at real data, he tries to estimate the remaining useful life. These are some cases, some different kinds of methodology. We have others, but all of these decisions are made based on the engineering assessment, the domain from Braskem, the domain specialist from Braskem, and together with the data science to choose what approach they will be doing, and a lot of testing, validation to have a good result before it goes live, before it goes production. So The third part I was saying after engineering data science was the software development. Gustavo said that the choice from Braskem was to have their own platform. So we modeled it and created a cloud platform that was able to run these models online with the data coming from different sources and having the dashboard that the operator could see, the dashboards that they can understand and can use the data to make better decisions. So we create a data, what we call a data aggregator dashboard and data aggregator platform. We take data from process, maintenance plans, operator logbook, maintenance notes, and it comes to a data ingestion. So this is the architecture of the platform. I won't be going too much detail about every module, but an important thing to talk to you is that some people think that doing cloud is just turning on machines on the cloud and virtual machines on the cloud. But here we are not using a single virtual machine. There are different modules, and using modules that Azure, in this case, have to leverage the construction of a modular platform and a serverless platform to run these models. So the data ingestion, model execution, and all that comes right after we receive new data. They are serverless and they can scale with the amount of data that we receive. So this platform right now, it gives almost 2,000 predictions per hour. We are receiving more than 50,000 data points per hour. So the platform, it goes the size as the data that comes in. So when we receive a lot of data, the platform grows and executes all the models, all the predictions, give the results, and then shrinks again. And the bill from Azure doesn't shrink with the data, and we can have a lot of parallel processing without paying a lot from the cloud. Okay. Sorry? Okay. Just to finish a little.
Sure.
So I'm just going really fast about these. We talked before why they choose these, and one thing to emphasize here is the DevOps and MLOps opportunity that a cloud platform and a custom cloud platform give us. So we can deploy a new version of the platform, new version of the models within minutes. So this is a really important thing when we are doing 54 equipment, 6 different plants, and a lot of users, and you have to have this central support looking at the health, monitoring the platform, and also be able to put new data, new models, retrained models rapidly to the cloud and rapidly solve the problems, and the users can use the platform. So here's just a couple of examples of the dashboards that the operators use for the furnace. Here's an alarm with the thresholds, a compressor dashboard that shows the exact cylinder that they have a problem, and a pump dashboard. So these two, if you have time later in the questions, I show you these two cases so the can speak.